Okay, moving on to section 2 or section 3 of chapter 2. We are looking at composite functions. So previously we've looked at taking these functions and adding, subtracting, multiplying, dividing them. So now we're going to take functions and put them in functions. Okay, so we're making composites of them. Okay, so let's start off with why we would use these composite functions. So with these composite functions, basically what would happen is that let's say we have two things that are related to something similar. So if we want to convert Fahrenheit into Celsius, okay, so if I know that my temperature is 98.6 degrees Fahrenheit and I want to know what it is in Celsius, the formula for that is 5 over 9 times your Fahrenheit temperature minus 32. And that's going to tell you what it is in Celsius. So if you plug in 98.6 into this equation and solve it, you end up with 37 degrees Celsius. Okay, so that's your temperature in Celsius. Now, from Celsius, you can also use Kelvin. Okay, so Kelvin is used more in science because you can use it as it's used in because there is no negatives in Kelvin. So the closer you get to 0, the closer you get to the absolute 0, basically meaning that's where everything stops, and basically the object will stop moving, all the atoms stop moving and everything. So you deal with negatives. So with that, since that occurs at about 273 point some odd Kelvin, we take our Celsius and we just add 273 to it. And so when we add 273 to Kelvin, or to our Celsius, that gets us our Kelvin. Now, what if we started off in Fahrenheit and we wanted to go into Kelvin, but we didn't want to convert it into Celsius and then do it again? So with that, what we would do is we'd take this equation and we'd plug it into the CT of that other one, creating a new equation, which is down here. Okay. So that's your composite functions, is where you take kind of two different formulas that are related to the same thing and you combine them to make one formula, so you don't have to do two calculations, you just have to do one straight calculation. Okay, so that's where it's kind of important for that. Okay, all right, so let's say you want to cook a pizza. So you've got a frozen pizza and you want to cook it, and it says that it has to be cooked at 400 degrees Fahrenheit, but you're at a science lab, and in that science lab the only stove that you have only cooks stuff in Kelvin. So now you've got to figure out, what temperature do I have to cook this in for it to be in Kelvin? Okay. So take a second, see if you can find out what the temperature has to be in Kelvin if you want to cook it at 400 degrees Fahrenheit. Okay, so with this, all you would have to do is you would end up taking this 400 degrees Fahrenheit and plugging it into that equation. So you end up with 5 over 9 times 400 minus 32 plus 273. And that is going to get you your answer, which is approximately 477.44 Kelvin. Okay, and it's actually 4444 repeating Kelvin. Okay, so that ends up being your temperature that you'd have to cook it at. Okay. All right, so fog engulf. So these composite functions that we basically just did, a way that we can kind of say it faster is just fog engulf. So with fog engulf, that means you're taking f of g and g of f. Okay. So you take f of g and g of f. Now what you do with these is that you take the second function and you plug it into the variable of the first function. Okay. Now sometimes with these also you will have a number afterwards, so let's say 3. Now the easiest way that I've found to do these is that you, instead of going left to right like normal reading, you go right to left. So you start with that 3, the 3 goes into the f, and then that number that you get goes into the g. So you kind of work backwards going the opposite direction. Okay, and that's kind of how you work your composite functions. Okay, This is what they look like if they weren't written with the little circles. So you notice how it's a little circle, open circle. That means you're talking about of. So f of g, g of f, instead of the multiplication. Okay, so f times g and g times f. Okay. All right, so let's say we have these two functions, and what I want you to do is I want you to find we'll find the first one. Let's find fog of the first one. So if we want to find fog, that means it's f of g. That means we take the g function and we plug it into the f function. So that means we'd replace all the x's. So if there's multiple x's, you replace all of them with the g of x function. So that means we'd have 2 times x squared plus 9. And then we would simplify it, which ends up being just 2x squared plus 9. Okay, so that's your f of g. So now take a second and find g of f. Okay, so with g of f, you're going to be taking the f function and you're going to be plugging it into the g. So that means you're going to go 2x plus 9, and then you are squaring it. Okay, and then what you can do is you can multiply that out. Ends up getting you a 4x squared plus 36x plus 81. Okay. All right, decomposing. So when you're decomposing compositions, basically what you do is you have kind of the final, and you want to break it up and find the f and g functions of the original. So let's say we have this function, hx is equal to 2x minus 3 to the 5th power, and we want to find f of x and g of x so that we can use f of g. For a way to once you do this, to check it, you just go back and do f of g and see if it gets you back to the original. If it does, then it works. If it doesn't, then it's wrong. So an example of this that we could have is as follows. f of x is equal to x plus 7 to the 5th power, and g of x is equal to 2x minus 10. If I were to take this g of x and plug it into here, into that x, I end up back at the original. Okay. Now, here's the thing with decomposing. Decomposing doesn't have one single right answer. You have technically an infinite number of answers that would work. As you see, the second one down there is a lot simpler to do for decomposing. F of x is equal to x to the 5th, while g of x is equal to x minus 2x minus 3. So when you're decomposing, you're just trying to find two functions. Okay, they don't have to be exactly perfect. You might do one, your friend might do a different one, but you still could get the same answer. Okay, so that's one thing you have to look out for. There's an infinite number of decomposing answers. Okay, but all you're doing is you're breaking it up. Okay, so if we have f of x and g of x, when do you think you would have f of x, or fog and golf, both are equal to each other, in which they also equal x? So take a second, see if you can figure out when fog and golf will equal to each other and they will also equal x. Okay. And the answer to this is that they have to be inverses of each other. Okay. So an example of this would be x. Let's go, I don't know, 2x. Okay. And 1/2 x. So if f of x is 2x and g of x is 1/2 x, those are inverses of each other. Okay. If you remember inverses, that's where we traded the x and y and we'd solve it through. And they're reciprocal around the line, y equals x. So that is when the g of x, or fog and golf, are both going to equal x. They would end up being inverses of each other. X squared and plus or minus square root of x would be another example of this. X cubed and the cube root of x would be another example of inverses. Okay. All right, so that's the end of section 3 in this chapter 2.